square will have 8 nodes. If we count them here, 4 from bottom, 4 from top, 8 nodes. That's what we have. Yeah, even its name is C3D8. Okay. LTO, even here, these commands have been explained well here. LTO HE command, it means that we will be meshing the set all, we had beam set, finally we had grouped all the geometry into beam set. So here all the set which is beam is going to be meshed, LT is going to mesh it, all of the set will be meshed by this type HE8. And then we will write mesh all, so all of them will be meshed. The LTO HE8 command indicates that we will meshing the set all with HE8 elements. The following element types are, yeah, here are the elements that I showed here also. This one, this square is element, and each element will have 8 nodes. So as I mentioned previously, that the cantilever beam will be distributed into thousands of this element that containing 8 nodes each. Okay. After this, we will type LT all HE8 mesh all. File, save. We will run it, preprocess. So if you focus that before meshing it, while we were opening the CGX, nothing was appearing. We had to type commands in order to make the points, lines, or faces appear. But now after meshing, automatically the whole geometry, right now the geometry has turned into a perfect model. Rot negative Z. Okay. And now okay, for the next video I will discuss about mesh in detail somehow. Okay, right now there is somehow a relationship between this mesh element and this model. Here, as I mentioned before, that this type of mesh element, as it's called HE8 from CalculiX, it's a square, or let's say it's a cube element containing 8 nodes. And now let's get back to this model. So if you remember, while we made this line as it corresponds to x-axis, the total length is 100 unit, but we divided the line into 4 major lines, and we divided each one of the major line into 25 line segments, and making, or let's say counting, the total division of 4 major lines will be 100. So here on this line and this line, or generally speaking, these two lines that corresponds to x-axis are consisting of 100 divisions, or 100 units, let's say 100 unit. Okay, and then for after sweeping that line, we sweep it or extruded it ahead of y-axis, as it's written here. X this direction, y is vertical, and z is normal to the plane or to the beam. So while we extruded this line vertically, corresponds to y-axis, we divided this line into 10 divisions, into 10 line segments. So here on this horizontal line we have 100 unit, and for the vertical line, where we have for the vertical lines corresponds to y-axis, again we have 10 units. And for the z, after stripping the surface while we extrude the surface normally to this plane, we divide it into 1. So now I will click here inside this black border, rot negative z axis, rot negative z. Why it doesn't work now? Okay, let me preprocess rot negative z. Okay, okay, rot x. I was wrong. Okay, and now if you zoom it, we see that here this line that corresponds to z, here z is horizontal, this line, which is thickness of the beam, has been divided into one unit. It's one, or in another words, I can say it's 1 millimeter. The thickness is 1 millimeter. Let's go back to rot negative z. Let's zoom out. Okay, and this one is 100 millimeter, the length, 100 millimeter. Let's think that's 100 millimeter, and it has been divided into 100 piece or 100 segment lines. Each segment is 1 millimeter. So 1 millimeter from here, 1 millimeter from there, from z axis, and also the width is 10 millimeter, let's say, and it has been divided into 10 segment lines. So each segment line is 1 millimeter again. So here that's the idea why we divided those lines into 25 and this one into 10 and this one the thickness into 1, because here the element that we are using it's a cube. So right now the length of the cube, all of them are inconsistency, all of them are same. So here this one is 1 unit, 1 millimeter, and this 1 millimeter, and the height also is 1 millimeter. So we have to figure out and visualize how to use elements and how to make divisions. These divisions are very good to ahead planning of mesh elements. Okay, viewing element address. Okay, now we can visualize it easily. Now this square, or let's say this cube, which has been illustrated here, can be seen here. Okay, now as I had discussed before, this had been divided into 10 elements or 10 segment lines. Each segment line is 1 millimeter, let's say 1 millimeter, and this thickness that corresponds to Z is 1, again 1 millimeter, and the whole length of the model was 100 and divided into 100 segment lines, that the length of each segment line is 1 millimeter, let's say this 1 millimeter, this one, this one. So right now the mesh is done. Okay, now the geometry of the model is done, mesh is done. We have already make a meshed model. It's completely done. Then we have to the final stage to finish this FBD file is by sending this file or sending the information of beam set or information of the mesh set into Abacus format page. So we will do it by send command, send beam. Beam is the name of the set. We want to send this set that its name is beam. As we discussed previously, whatever between set or beam and set C beam is a single set containing the all geometry of the model. send beam into ABQ abacus form. Okay, and then when there's something else, we will type root negative z, and it's for when we open CGX window, we want the model to be shown in this axis. We want it to be in this axis, rotation around negative z axis. We want it to be shown horizontally in an appropriate way. Then frame, we will type frame. Frame means when we open the CGX window, automatically the model will be fit into the CGX window. File, save. Okay, and now when you run it, that's what happens. If we look at the axis, Z axis is normal to the plane, so it's rotation negative Z, so it's normal to Z axis, negative Z axis, and then it's fit to the CGX window.